everybody. Thank you, Mr. Chairman, for the presentation. As you have already heard, today I will present you an experimental work with mortars made of recycled sand from construction and demolition waste. Why recycled mortars? As most of you know, the issue of the waste management is becoming increasingly important. From 2008, European Union emanated a directive that focuses on waste prevention and established that countries in the European Union should achieve a minimum recycling rate of 70% in weight for construction and demolition waste by 2020. As you can see in the this pie chart, the construction and landfilling sector is the biggest part by a waste generation point of view. So, the European waste legislation aims to move the waste management up a waste hierarchy in which prevention, reuse and recycling are the first three and important steps. And in general, the directive aims a life cycle approach. In this experimental work, we try to focus our research objective by a temporal point of view. In the short period, we try to replace in the mortars the standard sand with the recycled sand in order to ensure the same mechanical properties of the traditional mortars. While in the long period, we hope that we are capable to work with all the fraction of C&D waste in order to obtain totally recycled materials and so to answer to the directive on the waste management. In general, we found few literature about the final fraction of construction and demolition waste. And we found that there are almost the same problems. For example, in several studies, we found that there is a reduction of the properties such as flexural and compressive strength with an increase of replacement of recycled sand. Furthermore, there is a very big problem that is related to the workability of the mortars. In fact, the quality and the quantity of the finer aggregates strongly influence the rheological properties of the mortars. In this work, we work with the recycled sand provided by Cavit, a company a little far from Turin that deals with recycling materials by construction and demolition waste. And the purpose is to obtain the same granular distribution of the standard sand in order to partial and total replace the standard sand with the recycled sand. For this reason, both the standard sand and recycled sand were sieved in accord to the retained size mesh of the standard sand. So we sieved the standard and the recycled sand into 6 granular fractions. We decide 4% of replacement from 25% up to 100%. And so the sand packets have been realized by remixing of each granular fraction of standard sand and recycled sand, obviously to get the same granular distribution. We know that there is the workability problems, so in order to understand the behavior of our mortars during the mixing phase, a part of recycled sand was washed to try to limit as much as possible the problem of the greater absorption of water during the mixing phase due to the very fine and dirty fraction of recycled sand. After washing, it was not possible to collect a sufficient quantity of finer fraction, that is the 1% of total weight for the standard packet of standard sand. And for this reason, we replace the finer fraction with a similar one in commerce. In this case, we used a calcium carbonate filler. The recycled washed sand was identified by the acronym RSW. The work was done by a consequential steps, and so we cast 4 series in which some parameters were kept constant. For example, the percentage of replacement, so 25, 50, 75 and 100%, and we kept constant also the water to cement ratio equal to 0.5. We only varied the amount of superplasticity in our experimental casting of mortars. Every specimen was notched, and for each notched sample, the 3-point bending test was carried out, performed by controlling the crack mouth opening displacement with a clip-on gauge. After the TPB test, broken prisms were tested in compression in displacement control. By the TPB test activity, we obtain that, for example, in series 1, in which there is any addition of superplasticity, as you can see in the histograms, we obtain a huge decrease in terms of modulus of rupture. And you can see that over the 50% of replacement, well, there is the impossibility to cast the mortars. For this reason, in series 2, we decide to add the superplasticizer in the percentage of 1.25% with respect to the weight of the recycled sand. And as you can see, in this case, we obtain good results, more similar than the reference mortar one. This is a clear explication of that the mortar and the mortar with superplasticity, in this case is the dark green, are comparable in this load-CMOD curve, while the mortar without the addition of the superplasticity has a decrease in terms of modulus of rupture, as said before. In order to obtain a proper mix design, we decide to use the recycled washed sand, lowering the percentage of superplasticity addition. In series 3, we add 1% by weight of recycled washed sand. In series 4, we add 0.75% by weight of recycled washing sand. In these two cases, we obtain strange results. In fact, as you can see, for lower percentage of replacement, we obtain a decrease in terms of modulus of rupture in series 3 and even in the series 4. While for the higher percentage of replacement of standard sand with recycled washed sand, we obtain an improvement in terms of modulus of rupture. In order to obtain a total replacement of standard sand, we found that probably the 1% of superplasticity is the optimal addition. As you can see, in the series 3, we obtain an improvement than the mortar, the traditional mortar. The compression test activity follows the trend that we obtained in TPB test. As As you can see in series 1, we had a huge decrease in terms of compressive strength, while in series 2, series 3, and series 4, we obtain more comparable values related, obviously, to the quantity and the addition of superplasticizer during the mixing phase. In order to understand the trend of results, we decide to investigate the standard sand and the recycled sand by X-ray diffraction and scanning electron microscopy. By X-ray diffraction, we obtain that standard sand is obviously composed by quartz, while recycled sand and recycled washed sand presents like main element calcite and quartz, and the only difference between the two recycled sand, as you can see, is in the traces. In fact, recycled sand presents traces of gismondina and kaolinite, while in the recycled washed sand we obtain only traces of gismondina. So probably the washing process helps us to remove the finer and dirty fraction that is related to the kaolinite. By a morphology characterization, as you can see, the recycled sand and the recycled washed sand presents more indented and irregular grains with respect to the standard sand grain that are isometric and rounded. We investigate also the fracture energy of our specimen, and even in this case we obtain the same trend. So in series 1 we obtain a huge decrease, while in series 2, series 3, and series 4 we obtain the similar values, and for the higher percentage of replacement, an improvement too. Probably we could explain this enhancement of the properties, the mechanical properties and the fracture energy by a morphology point of view. In fact, probably the more quantity of angular grain for the higher percentage of replacement could give a better mechanical behavior that could be explained by an interaction, a more efficacious interaction with the matrix. To conclude, we obviously think that the partial and total replacement of standard cell is possible through a current mix design. In this case, we obtain recycled mortars with mechanical properties that are comparable to conventional mortars and even improved. For the long period, we hope to work with all the fraction of C&D waste, and especially to transform the problem of the very fine fraction into opportunities. In fact, the very fine fraction could be used as a filler in cement-based materials, or for example in self-compacting concrete, for example to evitate the segregation and so on. We hope that in the next 5 years we will be capable to answer to the waste directive. Thank you.